for about 22 years. And as an engineer, I tend to hop from mission to mission and have the great fortune to work on a variety of things, as you heard from Melissa in the intro. I spent I think of my formative years as a baby systems engineer on the Mars Reconnaissance Orbiter, which was a partnership with Lockheed Martin as a system contractor. I started on that mission in 2001, which is about 4 years before launch, and got to go through a lot of the process of refining the design, doing tests and analyses, and then into operations for a couple of years, which got us all the way to the planet, the 6 months of aerobraking that we did, and then about a year of good solid science and relay operations there before I moved on to a different mission. I joined Kepler just about a year and a half before launch. It launched in 2009. And while I'm not going to talk very much about Kepler today, if you don't know much about Kepler, and maybe those of you who are familiar with this conference have heard lots of presentations from the scientists over the years, do yourself a favor and go do a little bit of research into the amazing discoveries that Kepler has found. It really, as an exoplanet hunter, and an exoplanet hunter that's looking for planets that are in the habitable zone of its planet and elsewhere, but also of its star, also there. It's kind of revolutionized our understanding of how common planets are in our galaxy. I think that's going to be a highlight of my career for a very long time, no matter how long I keep working. Juno is one of the missions that I'm going to spend some time talking about today, so I won't say much about it right now, except that I joined the mission about 2 years prior to launch and worked on it for another 7 years after that, through the whole 5-year journey to Jupiter in a couple of years. Once we got there, we had lots of super fun adventures along the way. Then I put a stint in on Psyche for a couple of years from 2018 all the way to about 2020. That mission has not yet launched. They're gearing up to be launching later this year, heading out to visit one of the largest asteroids in the main belt in order to understand a little more about its formation. It's one that has a very high metal content, and there's some interesting theories out there about how it could form. Europa Clipper is the mission that I am on now as the lead flight systems engineer. I have been on this mission since 2020. I joined right at the beginning of the pandemic, about May of 2020, leading a team of about 40 systems engineers doing various things to help mature the design of that spacecraft and get us ready for launching in October 2024. And I'll be talking quite a bit about that one in this talk as well. So what is a system and what do systems engineers do? This is kind of a cartoon taken from the Mars Reconnaissance Orbiter, which is where I first learned how we do systems engineering here at the lab. Systems engineers work at a whole bunch of different levels on missions, but I'll talk a bit about the spacecraft one because that's the one that's the most easy to visualize and describe. So a system basically is a complex set of things that all have to work together in order to accomplish some kind of goal. And a system engineer needs to know a bit about all of the different functional areas that have to work together and make sure that across the whole cycle of the design, we are making choices that ensure they will all work well in order to accomplish the mission goals. And I'll give you an example. When you have a spacecraft like Mars Reconnaissance Orbiter, it needs to communicate with the Earth through some kind of telecom system. It needs to be able to orient itself relative to the things it's trying to measure, and also the sun and also the Earth. It has mechanisms that help maybe gimbal the solar array and the high gain antenna separately from the body, power system to get power to all of the components, propulsion to make sure that you're on the right trajectory that you need to go to, thermal, it's cold out there in space, and also hot when the sun is shining on you. So we have to keep things from getting too hot or too cold. And then the whole reason we're sending the spacecraft where they're going, which is the instruments, in order to take data to send back to the ground to the scientists to make all of their great discoveries. And as a systems engineer, I am never going to be 100% up to speed on every single aspect of the spacecraft. I have to rely very heavily on the subject matter experts who work in those areas. But there are decisions that we have to make early on in the design. For instance, should we have solar array? Should we have nuclear power? And the choices that you make, the pros and cons associated with both of those, end up driving a lot of other aspects of the design. Telecom versus attitude control is another good one. We want to have a very strong telecom signal so that we can send high data rate back to Earth, especially for some of these science missions that are sending back lots of data. You can do that by having a very strong amplifier that uses a lot of power, or in power limited missions like these that are going out in deep space, you can have less power for telecom and have a much tighter attitude control system so that you can put the strongest point of your signal directly on a deep space antenna and be able to get the link that you need and preserve a lot of power for other things like heaters and running the other components on a spacecraft. And I'll talk in a minute, perhaps the next slide, about the different aspects of a whole flight system design cycle and what it is that systems engineers are doing a little bit across that whole thing. So this is based on a Juno example. Missions start off with science questions. What are we trying to learn about the bodies that we are studying? For Juno, what is the core like? How deep do those storms on the surface go? How much water is in the atmosphere, et cetera? And then we come up with some kind of a mission design. In order to learn those things, to get the data necessary to learn those things, can you point a giant telescope from the Earth at that body? Can you have a flyby mission for that body? Do you need to go into orbit around that body? Should you go in orbit at the equator? Should you go into orbit around the poles? All sorts of things. And that's where engineers get involved in order to help determine how we get that information. And working with the scientists still, we come up with a detailed design of the spacecraft, and there are engineers who work with scientists to come up with detailed design of instruments, and you are working out ways to put them together as an overall system, which will be able to accomplish those goals. We go through the assembly and test process at every level, even down at the component levels. We're doing lots of testing and analyses, and you get to a point at the system level where you're integrating everything together and you're testing it in all sorts of ways in order to make sure it's functioning the way you should. I'll talk a little bit about how we try to think of all the things that can go wrong and deal with those as well. And then we button it all up on the top of a rocket and send it on its way. And we're in the operations phase where we're making our way to our destination in order to gather the data that the scientists need to answer the questions and close the circle all the way back to why we're going there in the first place. So as an engineer working on these missions, it is really valuable for me to know enough about the science that the scientists are trying to do so that if we have to make choices that could impact the science, we are well-versed enough to communicate with the scientists and do the right thing by the mission, as well as making sure that we're going to be able to execute the mission on time and on budget within all the resources that we have. And the science is just cool. That's the reason why I got into doing this kind of work in the first place. And so I think about the kinds of things that we knew about Jupiter before we sent Juno to go study it, and the kinds of things I like to talk to kids about. It's really big. It's got lots of hydrogen and helium. It has this cool red spot. You can fit 11 Earths across the middle, lots and lots of moons, including the 4 that Galileo discovered with his telescope, and rings, like all of the gas giants have. And then for Juno, in the beginning of that circle that I showed about the mission design, there are several questions that the scientists wanted to answer. And I won't go into these in detail. Juno's been around for long enough that you've heard this talk from many scientists at this conference and other places, describing all the details of the juicy things that they're trying to squeeze out of this spacecraft and the instruments to learn about the planet. But it's basically some things that'll help the scientists zero in on specific theories of how Jupiter was formed, its origin story, understand more about the interior and how it's structured in there, the atmosphere to map variations in the composition, understand how deep those storms go, and the magnetic sphere to kind of characterize that whole structure of its magnetic field. And as an engineer, the thing that is most relevant to what we're doing in designing the spacecraft, in my mind, is really this last one, the magnetic field. Jupiter's magnetic field is really, really powerful, and it traps charged particles from the solar wind and also from volcanic Io, and accelerates those particles to near relativistic speeds and creates this, I think of it as a donut of radiation around the planet. Jupiter is like a little bead sitting in the middle of this donut hole. And if we're going to go there and study it, we have to deal with this radiation environment and figure out how to have a spacecraft that is going to survive it and be able to get all the data and send it back to the scientists. And there are a couple of ways that Juno was able to do this by combining both the way the spacecraft was designed and also the way the mission was designed to not spend a whole lot of time down inside this zone. The spacecraft was launched in August 2011 from the Cape, and you can see how it was folded up with the solar arrays to fit in the top of the rocket. And then once the fairing ejected, the solar arrays were deployed out and then pointed at the sun. We didn't have a launch vehicle big enough to send us all the way out to Jupiter in one fell swoop with this giant spacecraft. You'll see how big it is in a couple of slides. So we sent it out on a path that took it out past the orbit of Mars. That's this red circle, all the way out. And about a year after launch, we did 2 deep space maneuvers where we fired our main engines for about half an hour each, spread apart by a couple of weeks. And that put us on a trajectory coming back by the Earth a couple of years after launch to do an Earth flyby gravity assist to give us a boost in our velocity to get all the way out to Jupiter about 3 years later. Arriving there, I think technically it was July 4th, local time, in 2016. And once we arrived, we went into orbit around Jupiter. And the way that the mission was designed in order to help us with the radiation story was, instead of orbiting Jupiter and spending a bunch of time going in and out of these high radiation zones, we kind of thread the needle a little bit and dip between Jupiter and the inside edge of this donut for each of the different orbits. And over time, the orbit kind of walks its way down. And so we end up spending more time going through the radiation belt. But doing it this way meant that the primary mission design was going to collect about 30 kilorad of radiation over the life of the mission. That is a number that I'm used to thinking about in terms of what the hardware can handle. But for those of you who don't think about radiation doses all the time, I've recently gone out and learned that when you think about how much dose a human body can withstand, there's a range of radiation doses you could get before it will totally kill you. But something around 1,000 rads or 1 kilorad is pretty unsurvivable. And so 30 kilorads is a pretty healthy dose for us to design the spacecraft to be able to withstand. This mission was originally designed to do about 32 science orbits, plus a couple of precursor orbits. And the mission was recently extended out to September 2025, adding about 42 more orbits, which will shrink the period and also fly by several of the moons. For those of you who have been following along with Juno and the discoveries that they've made, it's been some pretty exciting science that they found so far. A little more about the spacecraft. There were several engineering challenges we had to meet. I just talked a bit about high radiation and what we did with the mission design in order to try to keep that to a minimum. We also had this titanium vault tucked up under the high gain antenna where the sensitive electronics live, in order to knock the amount of radiation they would see in their environment down to something more like the environment that is typical around Mars. We are very, very far from the sun. I'll say a little bit about that and how big the spacecraft is, but about 5 times farther away from the sun out at Jupiter than the Earth is. And so we have these giant solar arrays to collect enough of that light to turn into power from the spacecraft. You can get a sense of their scale by looking at the folks here in these bunny suits. It's also very cold out there. So like most spacecraft you're used to seeing, we have thermal blankets and also heaters to keep the spacecraft warm. About half the power generated by the arrays goes to heater power. Very, very far away from the Earth. So we have this large 3-meter high gain antenna that we use to communicate back at the highest data rates. For the people who have really good eyes, you can also see a medium gain antenna and a low gain antenna. There are several other low gains around the spacecraft that we use to communicate at lower rates when the spacecraft isn't pointed directly at the Earth. And then getting into orbit, we had to get that Earth flyby to boost the spacecraft velocity to get all the way out to Jupiter. And then once we got there, we had to kill off some of that velocity and slow down enough to get captured. So there's a main engine on the business end of Juno that we fired for half an hour in order to slow down enough to get captured on July 4th, 2016. So the payload for real, because that's the thing that is the payoff for going there in the first place. Many, many instruments that you saw on the one slide are trying to gather enough data to allow the scientists to answer the questions that they had about this mission. Juno spins as it's going around the planet. You can almost think about it as pinwheeling around the planet multiple times during each science pass when we're closest to Jupiter to gather information from this whole suite of instruments in order to answer those questions. We also use, like many missions do, the telecom system, the high gain antenna, to do gravity science. And that takes advantage of the Doppler effect as the deep space network on the ground is listening to the signal from the spacecraft. The gravity variations in Jupiter changes the motion of the spacecraft in a way that we can detect in a Doppler shift and lets us learn some things about the interior structure of the planet. About the size of those solar arrays. So out at Jupiter, way less light than there is here. And when I give this talk for much younger people, I tend to tell them that they can imagine the sunlight spreading out the way they can imagine plastic spreading out on a balloon. You start with a balloon, you blow it up part way and draw a square on it, and then blow it up to twice that width. You end up stretching the square that you originally drew on there. So you end up with a square that's twice the length and twice the width, and you're stretching that same amount of plastic over 4 times the area. So an area that at the same size only has 1/4 of the plastic, or if you're thinking about it as the surface of light from the sun going out, you have 1/4 of the amount of light. Same thing, you go 3 times the distance, you have 1/9, 5 times the distance, which is where Jupiter is, you end up with just 1/25 of the light out there. And in order to power the spacecraft, even though we do our best to make sure all of our components are efficient and don't need a lot of power, you end up needing a very large solar arrays. These solar arrays all the way out at Jupiter is about 66 feet across, 20 meters in diameter, generate about 530 watts of power all the way out there at Jupiter. About half of that is used for heat, and the rest of it is used to power all of the instruments and do all the telecom and all of the engineering equipment on board the spacecraft. So you wind up with a spacecraft that is about the size of an NBA basketball court in order to generate that amount of power, which is about 1/3 of a microwave, which is kind of crazy when you think about it next time you're at home warming up your leftovers. And with very complex spacecraft like this, we have to figure out a way to find all the problems that can go wrong with it, and design them out or figure out how the spacecraft can deal with them. And this is one of my favorite systems engineering kind of processes and practices to go and apply, because it allows you an opportunity to just do that creative thinking. And in order to build out a fault tree, for example, we would start with something like launch. We need launch to be successful. And for launch to be considered successful, when you get to the end, you need to be power positive, you're making power and not running out of power. You need to be thermally stable, nothing's getting too hot or too cold. You need to be in communication with the spacecraft, you need to be on the right trajectory to where you're going, and so on and so forth. And so we take those things and we turn them around. What could keep us from being power positive? Well, maybe my solar array did not deploy. Maybe my battery is not charging, and so on and so forth. And for each of those things, you break it down into smaller parts. Why might my solar array not have deployed? Maybe the command didn't go out. Maybe a hinge got stuck. Maybe a release mechanism didn't fire, and so on and so forth. And you keep doing that across all of these different areas, and you end up with hundreds of these little leaves for launch, for orbit insertion, for all of the major activities that you need to do. And for each one of these things, you go through this thought process of figuring out what is it that we can do to literally design it out so it cannot happen? Or what do we do such that if it does happen, the spacecraft can deal with it? And a lot of the things falling into that second category is that we have backup parts for everything that's really important. We have 2 star trackers and 4 reaction wheels, and we only need 3, and 2 inertial measurement units, and so on and so forth. And then for each of those things, you have to then prove to yourself that what you said was going to mitigate that fault is actually gonna work. So that usually involves some kind of analysis or some kind of test or some kind of inspection. And it's a tremendous amount of work at the systems engineering level to go through this process, find all these leads, and then prove to yourself that it's all going to be fine. And you would like to think that having gone through all of that effort, and also something called a failure modes effects criticality analysis from the bottoms up, you take every single component and say, if every single tiny piece failed, what are the symptoms, and would you notice those symptoms, and what would you do about it? It's kind of a top-down, bottoms-up approach. You would like to think that in flight, we would have found all the things and there's never any issues, but that is absolutely not true, because these spacecraft are so complex. Sometimes small things will slip past us and we get a little bit surprised in flight. And so that's another interesting task for systems engineers, is that we have an opportunity to play this mystery hunt game. When something goes a little bit sideways of what you expected in flight, you get to go on this discovery path to determine what happened, why did that happen, what can we do about it? My spacecraft is 300 million miles from here. I can't send an astronaut to go whack it with a wrench. We have to do the investigative work, figure out from the symptoms what the constellation of options could be that happen, and then what we can do about it, oftentimes in terms of software changes or adjusting the way in which we do activities or changing the order of commands in order to make sure our mission is still going to be on track. And we had some fun times with Juno in the 5 years along to the planet, and also once we got there. Right off the launch pad, there were a couple of components that were much warmer than we expected them to be at 1 AU. And so we wound up doing some investigations into that. One of the components we put into this thermal vacuum chamber, shut the door. There's a window in here that you can't see. And we shined some artificial sunlight on it in order to simulate the conditions in space as much as we could. And that allowed us to adjust our thermal model to be more like what we saw on the ground, and then make predictions of what the temperature of those components would be farther downstream. And fortunately, it turned out for both of those cases, they were not going to get above a temperature that was going to be problematic. Earth flyby was another fun time for us. The way the original mission was designed, we were going around Jupiter at the poles. And if you imagine, you guys are the sun watching me, and Jupiter is orbiting kind of in a circle around my head, around my face. We never were going to be in eclipse. We're never going to be behind Jupiter with respect to the sun. But we knew we were going to be behind the Earth with respect to the sun during Earth flyby. And that was a situation where we were going to be relying on our batteries for about 19 minutes until we came out the other side. These batteries were sized for like 2-hour eclipses at Jupiter. Didn't expect any issues, but we did have a fun surprise where the spacecraft did something a little bit different from what we had expected, and turned off all the instruments and entered a mode we called safe mode and called home to tell us it had a problem. And that is us in the JPL side of the mission support area, standing around looking a little bit perplexed on that day. Fortunately, we were able to figure out fairly quickly what that issue was and get things back on track. And it turned out to be a little bit of a blessing in disguise, because we updated the way that we were doing some of our power analyses in a way that was going to hold us in good stead once we got all the way out to Jupiter. Not everything goes sideways in operations, though. Jupiter Orbit Insertion Day is an example of one that went off without a hitch. For this one, I was out in the mission support area with our colleagues in Lockheed Martin. You can see here, one of my colleagues had on his 4th of July hat because it was that holiday for us. And the spacecraft fired its engine for 35 minutes the way that it was supposed to, and all the things leading up to and after that. It was a very exciting day to put the spacecraft in orbit after years of time and effort by hundreds of people at JPL and Lockheed Martin and all the institutions for the instruments, and vendors who provided hardware for us. It was just a great payoff. And then once Juno has gotten there, it's been in orbit now since summer of 2016. There have been any number of fantastic discoveries that have been made, papers that the scientists have been able to write to describe the lessons that they're learning from the data that they have gotten back. I'm not going to go into detail of these, just inviting you to go off and take a look for those of you who aren't familiar with the details. And then, as kind of a layperson, not scientist, engineer, but I'll tell you some of the things that I was the most excited about in hearing back from the scientists and the spacecraft. Number one was that the way that the North and the South poles looked was so different from what I had expected based on just the normal view we tend to have of Jupiter from the spacecraft that go by its midsection. I remember being in the audience in the science team meeting where the folks from the JIRM team, the Jovian Infrared Auroral Mapper from the Italian Space Agency, put up one of their first images, not exactly this one, but their first image of what the poles look like in infrared. And the whole room burst into applause. It was so exciting to get to be among the first humans seeing for the first time what the poles looked like. And that there were these crazy storms, like over 1,000 kilometers wide, especially this at the North Pole, where there's these 8 storms in this oddly symmetric pattern up there. Like, that was just a really cool first. One of the things the scientists were interested in is how deep the storms go. This is one of my favorite compilations that was put together quite some time ago with a visible image from JunoCam layered on top of microwave radiometer data, which gives you a sense of areas that are warmer, areas that are cooler. And you can see all the way down, as far as this instrument can measure, there were differences across the Great Red Spot. So that storm has some pretty deep roots. And I think there was a paper written later that was talking about an estimate for a lower bound of that too. So scientists have a decent idea of what's going on there. And these images I just include because they're cool. I always think about Jupiter as this place that has these tan and rust-colored bands, but with all of the really cool images JunoCam has been sending back, it's just a place that has a lot of complexity, a lot of color. And I love the fact that the JunoCam data, the raw data, is posted, and regular citizens from anywhere in the world can log on, grab that data, image process it, and repost it. And that's why you see the image credits include the names of people who have been doing that on their own time. And for those of you who want to see more information about Juno, feel free to visit at the mission website and go to the Juno gallery to see all of the gorgeous images that are coming back, and links to all the papers and presentations that the scientists have made about the exciting discoveries. Now I'm just going to spend a little bit of time talking about another cool destination, pun intended, in the Jovian neighborhood, which is the moon of Europa. The Galilean satellites of Jupiter. Galileo, way back in 1601, I think it was observing Jupiter in his telescope and saw these bright points that I think he originally believed were stars, but they were moving relative to Jupiter. And eventually he realized that they were bodies that were in orbit around that planet. Those ultimately were Io, Europa, Ganymede, and Callisto. And the Galileo spacecraft was able to visit Jupiter back in the late 90s, early aughts, and sent us back this cool image and a couple of others of the moon Europa. Why are we sending another spacecraft back to Europa? Again, I'm an engineer, but I'm really interested in why the scientists are going to do things. And so what I've learned in my time on the mission is, and I stole these slides from the scientists, of course, is that the scientists believe that underneath this ice shell, there is lots and lots of liquid water above a rocky mantle and then down to a solid core. And compared to Earth, Europa has way more water than Earth, about twice all of the water on the Earth combined in this layer of a moon-wide ocean on Europa. And for me, I always thought it was like, how do we know that there's water down there? And my understanding is that when Galileo visited Jupiter and had his magnetometer taking data around Jupiter and also near Europa, it measured a bend, a perturbation in the magnetic field around Europa. And the best explanation that the scientists can come up with is that there was some kind of conductive liquid under there. We know that the Earth's tides perturbs the Earth's magnetic field. And so briny water of some sort is the most likely culprit for causing this signature in the magnetic field. And then the next question I ask myself, and that all the kids ask me when I talk to them is, okay, you just said that Jupiter is 5 times farther away from the sun than the Earth is. How can there possibly be liquid water out there? And the answer is tidal flexing. The orbit of Europa around Jupiter is not perfectly circular. When it's closer to Jupiter, the gravity pulls on it harder. When it's farther away, the gravity is a little bit weaker. And so that's essentially stretching and releasing and stretching and releasing the moon, causing lots of friction in there, which is enough energy to heat a layer of water under the ice. Why do we care about that? And that's because here on Earth, whenever there's water, there is life. We know that, or the scientists strongly suspect, maybe many of them would say we know, that there is more water than all of the Earth's oceans combined. There are essential elements there from formation and impacts that we can tell by the observations that have been made of it to date. One of the things that Europa is going to do is get more information about the surface composition and also any particles that we can fly by with the spacecraft. There's lots of chemical energy, pretty warm down there. We talked about why there's so much water there in the first place. And also, even though there's weaker sunlight out there, there's still sunlight, and the radiation from Jupiter makes changes in the chemical composition of the surface. And it's been stable. It's been simmering down there like that for about 4 billion years. And on Earth, when we think about extremophiles, way down at the bottom of the oceans, where it's far too much water for light to be able to penetrate, there are hydrothermal vents with energy from the heat inside of the Earth, creating these water jets, providing energy to drive life forms in that environment. And so there's the wonder that something like that, at least enough to support microbial life, be going on down under the ice in the water of Europa. So I'm very happy to be part of a mission that is planning to go out there and grab a lot of data in order to help the scientists answer some of those questions. Europa Clipper is going to launch in October of 2024. The dates here are day, month, year, by the way, and a little out of date. I think the opening of our launch window right now is October the 10th. So we'll launch it from the Cape in 2024. Similarly, we're going to do like Juno did, a flyby, but we're doing 2. We're going to go off on a trajectory to Mars, do a Mars gravity assist, which will kick us back by the Earth a couple of years after launch for our final boost to get all the way out to Jupiter a few years after that. It's about a 5.5-year journey, which we call the mega trajectory Mars Earth gravity assist. and we'll arrive in 2030 in order to start our science tour. And similarly to Juno, rather than orbiting directly around Europa, which is nestled in that nice little radiation donut around Jupiter, we're going to be orbiting around Jupiter technically, but doing multiple flybys of Europa at fairly low altitude. I think the majority of the 50 or so flybys we're going to do are below 100 kilometers in order to let a suite of instruments gather lots and lots of information about that moon. For the spacecraft, we had a lot of very similar challenges, radiation at Jupiter/Europa. And so similarly to Jupiter, to Juno, we have an avionics fault that we're using for some of the sensitive components. This spacecraft, because Europa is in the radiation belt and we have to go deeper in than Juno did in order to get our science data, is going to take a lot more of a radiation dose than Juno did. Juno's design radiation dose is something like 30 kilorads, I had mentioned. For a Europa Clipper inside the vault, the design intent is to get it down to about 150 kilorads, so 5 times that. Outside the vault will be even higher. We're very far away from the sun, just as we were, since we're going back to the same neighborhood. So we have large solar arrays, about 100 square meters in area. You'll see, I might have included an image of what this one looks like. The edges of this hang off a little bit over the edges of a basketball court. It's about 30.5 meters end to end across the whole spacecraft. And instead of just relying on electric heaters, we have a heat redistribution system with fluid-filled pipes that run around the avionics vault to capture some of the waste heat from the components in there, and then use that heat to warm up the rest of the propulsion module. A long way away from the Earth, so similar to Juno, we have another 3-meter high gain antenna and lots of other antenna that we use when the spacecraft is in different orientations. And getting into Jupiter orbit, a little bit different from Juno. We don't have a single main engine, but we're going to use several of the thrusters that we also use for just attitude control and burn them for about 6.5 hours in order to slow down enough to get captured by the Jupiter gravity once we get there. For the instruments and science objectives, lots of stuff that the scientists want to learn about the planet. There's kind of 3 main thrusts: ice shell and ocean. How deep is the ocean? How thick is the ice shell? Are there hot spots? Or there are pockets where you have a little bit of liquid water that's closer to the surface. We want to learn that and many more things about it. And we have several instruments that are geared to do that. One of my personal favorites is the ice penetrating radar, which will help us plumb the ice shell. I want to learn more about the composition, and we have spectrometers that are going to be able to tell us more about what kinds of materials there are on the surface. And then a bit about the geology. There's all of these huge features that to me look like cracks in the ice. Lots of things that the scientists want to understand about that. And one of the interesting things is how things are changing over time, which kind of cuts across all of these different elements. And so similar to Galileo, we'll have a magnetometer on board, which is going to help us sense the ocean properties. There'll be a couple of cameras, a narrow and wide angle ice camera that'll let us map the landscape in 3D and color. I talked about the spectrometers. We'll be using the telecom system for gravity and radio science to kind of understand more about the ice shell and ocean depth, and also measuring tidal flexing. Don't want to leave out any that might be people's favorites, but a whole suite of instruments festooned around the spacecraft. So they're going to gather lots of data to help us understand this exciting moon better. Where are we now with Europa Clipper? We are in the process of integrating hardware. Our first instrument, the ultraviolet spectrograph, has been delivered to JPL, and many of the components that are being built by our partners at Applied Physics Laboratory in Baltimore, the propulsion module, the radio frequency module, are ready to be shipped soon, and we will be assembling them at JPL while running through final suites of testing all of our V&D, finding and fixing little issues as you do on spacecraft that's complicated, on our way towards a launch in October 2024. And if you'd like more information about the mission, you can visit the mission website here, which will vector you off to the places that have mission news releases and also a really nice 3D model you can find of the spacecraft, and spin around to learn more about the different parts of the spacecraft and all the instruments. And that's the end of the talk. Hopefully I still left us a little bit of time for Q&A. I will stop sharing.
Thank you, Tracy. That was fabulous. So we are now ready to take questions from the audience. So those online can ask questions, and on YouTube, Kristen will read out the questions, and on Vimeo, have I got it right? Vimeo, Jen Glass will ask the questions. And if we have anybody here in the audience, we have 2 microphones set up. And I know that there is one question available in Vimeo, but maybe in the time that we have, maybe I'll ask one quick question. Tracy, would you know, you showed those pictures of Juno. You mentioned cooler and warmer temperatures. Do you have any clue what those cooler and warmer temperatures might be like?
Oh, you know, I used to know the answer to that, but unfortunately, I don't have that plugged into my brain. I do think that if you do a search for Jiran, Jiran, Jupiter temperature, you'll probably get something that pops right out on that.
Okay, thank you. I could do that. So we have one question here at the Hilton. So,
hello, Garrett Roberts Kingman here from Ames Research Center. I was wondering if there was anything that you as an engineer wish that the scientists kept in mind from the earliest stages of developing a mission concept.
Yeah, is there anything that I wish that the scientists kept in mind from the earlier stages of development? That's a good question. I'll answer it in this way because the project scientist on Juno, Steve Levin, and I have given a couple of fun talks on this topic, which is the healthy interplay between scientists and engineers, which is engineers tend to be a little conservative, right? We have this spacecraft that we pour all our blood, sweat, and tears in. We're sending out into the scary environment, and we want it to be able to last for a very long time. And so we tend to be a little bit hesitant to push the bounds of the spacecraft capability beyond what we originally designed it to do. But scientists, oftentimes, they spend their whole careers trying to get an instrument on a spacecraft so that they can again get back data and solve these questions that they want answers to. And so for them, they're like, we have the spacecraft and these instruments all the way out there. Can we please just like do a little more, go a little farther, or turn the spacecraft a little farther than we said we would, because you can get all of this great data from it. And so they are not wrong, but they also have a vested interest in making sure that the spacecraft stays healthy and safe for long operations. And so we end up having a really good interaction talking about how much risk there might be in doing some stuff like that, how much benefit there could be, and finding a good line that is acceptable. So I tend to think about that from a late mission phase thing in operations. And I think that some of that same mindset can and should play in the early development and design. And back then, it's more in terms of how complex do we make the mission in order to get the most science possible versus trying to make things a little simpler so that it's more robust later.
Tracy, can I have you turn on your camera?
Yeah, so here's what's going on. I am using my camera from one computer and my audio from a different computer. Let me see if I can turn on this one and then turn off the other one here. Yeah. Slightly different background. There we go.
There we go.
Is that better?
Wonderful.
Yeah.
Okay. Kristen, do you have the next question?
Yes, we have a few questions from online. The first one is, will the James Webb Telescope have a role in exploring the Jupiter system?
Yeah, and that's one I'll have to say sometimes that we engineers can be a little head down in our own little bins of things. I do not know much about the James Webb Telescope and what we're intending to do with the data. So I got to say, I got nothing on that one.
No worries. We have another question as well. What is the expected life expectancy of the orbiter or the length of the mission?
We're talking about the Europa Clipper mission?
I believe so,
yeah. Yeah, the planned mission duration, we're going to arrive in like April of 2030, and the primary mission duration is about 3.5 years. I think that it has, just like Juno, we always have to build spacecraft to be robust, to make sure they're going to last their entire mission lifetime. And so there's some possibility, usually when you get near the end of a mission, the scientists and the engineers work with NASA headquarters to put together a mission extension proposal to see if it can last longer. So definitely 3.5 years after the mission starts, and TBD how much longer after that.
Great.
Excellent.
And we have another question here in the auditorium.
Hello. First of all, I would like to say that fantastic talk. I thought it was very exciting. I'm Arish. I'm a high schooler doing at Georgia Tech. And I wanted to ask, what kind of challenges do you foresee with the Europa Clipper mission, which might cause, big problems down the line, or what kind of challenges they're facing right now?
Yeah, and I won't go as far as to say it might cause big problems, but it's the standard challenges that we have with all spacecraft at this level of complexity. You saw the whole fault tree description of the things we try to envision that can go wrong and all of the things we do in order to design them out. One of the things that stands high on my list of things to think about is just the radiation environment in general, because it is so much stronger than Juno experienced. But we knew about that. I've only been on this mission for a couple of years. People knew about that years and years ago when it was proposed. So I've taken many steps to make sure the design is going to be very robust to that. But in my 20 years at the lab, the things that I have learned is it's the things that are newer and different, which are the places where you have the most opportunity to find challenges to go and resolve. So that's one that kind of stands out for me.
Okay, thank you.
Mm-hmm.
And then we've got one more online question, and that is, could you speak more about nuclear power on outer space missions?
Yeah, so I'll just say a little bit about it, because you may have noticed all the missions that I have been on are all solar powered. So that's where most of my experience lies. I know that one of the things that is nice about nuclear power, that as used on the rover missions, as was used on Cassini, is that it's a pretty steady source of heat that you can use. So similar to the way that the Europa Clipper spacecraft will use the fluid-filled loops to pump waste heat around to warm other parts of the spacecraft. On nuclear power missions, you can totally do that, and you know that you'll always have the energy for that. One of the things that I know is beneficial about nuclear power is you don't have to always think about where are your solar arrays? Are they pointed at the sun? If your spacecraft has a problem with its attitude control system and goes off point, well, now you don't have enough power. You don't have to worry about that with nuclear systems, which is nice. But then there are other things that you do have to worry about. There's just pros and cons on both sides. And so we always look at the specific goals of the mission we have, the specific kind of parameters of the mission to determine which one is better. But it just has turned out for me, all my missions have been solar powered so far.
Wonderful. And Jen, do we have any more questions coming in? I don't know if you can hear that.
I believe you have one guy.
Hi, this is Christina Buffalo from Georgia Tech. I wanted to thank you so much for a really fantastic presentation. I'm a scientist. I have very little engineering background, so seeing this perspective was so cool. I'm wondering if you have any, I don't know, favorite detection methods or measuring tools or systems or something that you used in your mechanical engineering training that you wish could be miniaturized and sent into space that we have yet to do.
Oh, wow, that's a great question. No one has ever asked me that before. Is there something I wish we could miniaturize and send into space that we have yet to do? I don't know about that. And maybe it's because I have been so spoiled in terms of talking to scientists like you and the kinds of things that they want to learn, and being always so amazed by the types of inferences they can make by the stuff that we already have. I might have to say some things about what I've heard scientists say they wish they had. One of the things that was cool for me way back in my early career at the lab, they took a bunch of us engineers out on a class field trip wandering around the dry riverbed arroyos at JPL. It was a geology for engineers class that was taught by a couple of the scientists who work on the rover mission. And they were explaining to us the kinds of things they, as geologists, want to understand or can draw conclusions from based on the terrain, what kinds of things they want to see, what kinds of things they want to measure. And I was trying to remember if there was anything specific that they said that made me go, if we had this thing or that thing and we could put it on a planet, then it'd be easier for us to learn stuff. But yeah, nothing specifically comes to mind, but that's a fun thought experiment to do. I'll think about it and be ready for that if someone asks me that later.
Thank you so much.
And we have another Vimeo question, and that is, of all the missions you've been involved in, was there one that was more challenging or more satisfying or stood out in some other way?
Yeah, and that's like for people who have children, it's like, I love all my babies the same. And the thing for me across all five, I'm going to cheat and just give you the long answer. The thing that is special for me about Mars Reconnaissance Orbiter is that was the very first mission that I was ever on. And so we'll always have a little soft spot in my heart. My first launch, my first orbit insertion, my first time being an ace on console at 3 in the morning during 6 months of aerobraking, like all of those things were great. And since I was on that mission for 6 years, I made a lot of friends with the people that I work with, and it's very cool to get to bump into those people later on in your career. So that one will always have a soft spot. My next mission, Kepler, just in terms of the sheer magnitude of paradigm shift of our understanding of the universe, that one is probably going to take the cake for a long time, because our understanding now that on average, right, most stars have a planet, or some have none, but some have many. The idea that you look up in the night sky, like at that Milky Way picture that I showed before, and the sky is basically dripping with planets is ridiculous to me. And it's really, really satisfying to have been a tiny part in helping to get that mission to the launch pad so that scientists can make those kinds of discoveries. And then Juno is another one that's great. If you made me pick a favorite planet, it would probably be Jupiter, because come on, it's just really cool. And getting a chance to be part of a team that sent a spacecraft out there to learn so many things about it is great. I still love that image of the North Pole in infrared with all of those storms. It's very, I didn't expect that kind of science, which is cool to see. And I was on that mission for 9 years. So again, made lots of friends, almost family members of some of those folks. Went to Costa Rica with my boss and his wife and my husband and a bunch of geology students once. So that one will have a soft spot too. Psyche was special to me because it's such a different technology than I was used to. That mission was using low thrust instead of the usual chemical propulsion that I'm used to. And there were so many different challenges with respect to how we designed a spacecraft and understood the error sources, and we're planning to have those engines on all the time in order to hit our maneuver execution errors. Like all those things will remain in my mind as just fresh, different challenges that were also really fun. It was a great team of people to be working with. So I will be happily watching and keeping my fingers crossed for the folks who are still working to get that mission off the ground and off to its destination. And then Europa, just because when I, again, not as a scientist, so sorry, I have my favorites, think about the places in the solar system that are the most intriguing for life, I can't help but absorb the messages from all of our science teams that Europa is off the charts, just a cool place to go and study. And I'm hoping for a similar game-changing shift in our understanding of things here about in our solar system and ocean moons in general, once we have the spacecraft out there and gathering data. That's a long time from now, but I'm patient. And based on my Juno experience, that 5-year cruise is going to go by really fast.
Can I squeeze in one more question? So, Tracy, I read that you really like science fiction, and one of the things that I've heard a lot here this past week is that there are many people who were inspired by science fiction. I was wondering if you could speak to that.
Yeah, to me, science fiction is one of those things that just everyone's going to watch TV, right? And it's something that is a way to have a different vision of what the future might be like in a way that just inspires us to be creative. I mean, I totally wanted to go have a job in space so that I can make the world look more like Star Trek. I didn't have any illusions we were going to be on the Enterprise and finding aliens and all that stuff, but just a little baby steps in that direction is very, very exciting for me. And there's all sorts of really interesting collaborations, especially living in Los Angeles, that you get to see between scientists and scientists and engineers, people who are in STEM fields, and folks who work in the entertainment industry, because they know that it's even more fun for people to watch films that have more realistic science, that have more realistic characters in the movies, that have more realistic plot lines that are related to science. One of my favorite recent movies was Interstellar. I also really love The Martian because there's so much realistic engineering in it that it's a great way to have fun with science and also think about how we can apply it to the real world. Not that applying it to the real world isn't fun too. Yeah.
And there was one question that Jen Glass asked, if you have any words of advice for any young people who might be listening.
I do. Oh, so much. We could have spent a whole hour just talking about that. I think the things that I like for young people to know is that, number one, people always say, find your passion, follow your passion. Okay, great. But how do you do that? And then young people have all this stress on them. How do I find the thing that I'm going to love and make sure I'm doing the thing that I'm going to love? And my own personal origin story is a little bit annoying to me because it sounds so linear. I grew up on science fiction. I wanted to be an engineer. I work at NASA now, but it does not work that way for all people. And I want folks to know, I know people who work at the lab who started off in music and synthesizers and then realized they could use that technology on science data. And people who started at the lab doing science stuff and then went off to go do something completely different. Like, I want young people to know that your whole life is an exploration, and you don't have to feel like you have to be on this one track and go that way forever. You can take a left turn and a right turn, like have some fun with it, and don't panic that you're not going to get it right the first time.
Excellent advice. Wonderful. Well, can you all join me in thanking Tracy for this excellent discussion this evening? Thank you so much.
Thanks for having me.